with the first derivative test, there will naturally be a second derivative test. Can you erase something over here? What is it there? SDQ. 50 minutes. 50? Don't care? Yeah, actually not any little stuff. Is it 15 minutes? I erase this part. I don't know how. 50 minutes. SBQ. Is it? Okay. Okay, let's go back 3 minutes. Okay, clearly, Chloe, we can hear you loud and clear. Yeah. Can share with Libby. And then ellipsis. Is there something wrong with Ashley's hair? Or are you evolving to become an ape? Going against Darwin's principles? Okay, now, chapter 14, nature of stationary points. Okay, first of all, we need to understand what are stationary points. Okay. So, actually for stationary points, we have actually touched upon it before already, just that we didn't give a name to it. Stationary points is a generic name for 3 things: maximum point, minimum point, as well as a point of inflection. Okay, so stationary points refers broadly to 3 different things: maximum, minimum, as well as point of inflection. Okay, for maximum and minimum point, when we did our E-maths last year, okay, you might recall that we have drawn tangents for maximum and minimum points. And for tangents at maximum and minimum point, okay, they would be a horizontal straight line. Okay, and with a horizontal straight line, that means their gradients are equals to 0. That means dy over dx is equals to 0. Okay. Very rarely we will be talking about tangents at a point of inflection, but strictly speaking, when we talk about point of inflection, okay, the tangent itself is also having a gradient of 0. Okay, although very rarely we won't be talking about it. Okay, let me describe for you what a maximum point is supposed to be. Okay, so for a maximum point, right, how we define it, okay, using calculus concept, using our differentiation concept, or the concept of gradient, okay, looking at the maximum point over here and understanding how the tangent is being drawn, we look at the tangents that will be on the left of the maximum point and on the right of the maximum point. On the left of the maximum point, okay, your tangents will always be upward sloping, right? They'll always be upward sloping. Whereas on the right of the maximum point, your tangents will always be downward sloping. Okay? No matter how you draw the maximum point, this will definitely be true. Okay? So that means that your gradient, your dy over dx, will change from positive to negative. Okay? So as it passes through the maximum point, it will change from a positive value over to a negative value. Right? Similarly, drawing that same idea to your minimum point, on the left of your minimum point, your tangents will always have a negative gradient, downward sloping. And then on the right of the minimum point, your tangents will always be upward sloping, hence it will be positive. I'm just writing in shorthand over here, positive, negative, negative, positive. Okay, so for minimum point, the gradient actually changes from something that's negative and then over to positive. Okay, what about point of inflection? Point of inflection is not found in every single function, or most commonly found, or rather it is most commonly found in your cubic function. So in this case, it's a cubic curve. Okay, usually it is between your maximum and minimum point. Okay, so this point of inflection, right? Okay, it is where your gradient itself doesn't have any changes at all. So on the left of your point of inflection, in this particular case, it is downward sloping, so negative. On the right, it is still downward sloping, so it's negative. It is possible, okay, for your point of inflection to be found over here, such that your gradient is always positive. On the right is also positive as well. Okay, so that is for your point of inflection. Okay, so point of inflection is called point of inflection because the gradient, okay, before and after doesn't change in the sign itself. Sign meaning to say the positiveness or the negativeness, if there's ever such an English word. Okay? The first derivative test, which is a test to help us determine whether a point is it maximum, minimum, or point of inflection. Okay? So typically when it comes to your first derivative test, we will be drawing a table. Okay. Okay, so usually in our first derivative test, we have a table that looks something like this. Okay, there will be 4 columns. First column being these titles over here. And then the remaining 3 columns needs to be filled up such that the x-coordinate of that point is placed over here. Okay, and then we have our A minus and A plus. Okay, I'll talk more about it later on when I show you an example. Okay, about what this actually means. Alright, so in our first derivative test, we will be investigating that particular point. Okay, how the gradient changes, how the sketch of the graph is supposed to look like. Okay, or sorry, sketch of the tangent. Okay, so maybe to be specific, sketch of tangent. Let's start off with example, textbook page 48. So in try 1, you're given this graph for this function when x is more than 0. Part I, we want to find out what is dy over dx, which we already know how to find. So given that function there, our dy over dx is equals to 6x minus 6. Okay? Then in part 2, they ask you to find the coordinates of the stationary point. Okay, so we understand that for stationary points, there are points at which your dy over dx equals to 0. Okay, it must be in a function, a curve like that. Okay, for a straight line itself, there's no maximum or minimum. There's no stationary points to talk about. Okay, so to find the coordinates of the stationary point, our dy over dx must be equals to 0. In other words, 6x minus 6 equals to 0. Hence, we can solve to find out what is x. Okay, but I want the full coordinates, so I must find out what is the y coordinate. So substituting the x coordinate into the curve, because your point must lie on the curve, therefore your y value is negative 2. And therefore, 1, negative 2 is the stationary point. Okay. In this particular question, we are not able to, if not given the graph, so if the graph is not given to us, we are not able to tell whether 1, negative 2 is it a maximum, minimum, or point of inflection or not. Okay. So this brings us to our first derivative test. Okay, I just want to extend this question since we are on it. Part 3, determine whether the point is, sorry, let me rephrase it. Determine the nature we want to determine the nature of the stationary point. Okay? So very clearly from the graph, I know that it must be minimal. But what if the graph is not given to us, which is going to happen for most of the cases? Okay? So that's where we will be making use of our first derivative test to help us determine whether it's a maximum, minimum, or a point of inflection. Okay, so how do we use that? Okay, so with the point 1, negative 2, we construct our table. Okay, as I mentioned earlier on, there will be 3 main columns. Okay. The one right in the middle, for x value, will actually have to be 1. The x coordinate of the point in discussion. Okay? to the left of that value of 1, I will put 1, okay, minus at top right hand corner, like as though it is a power itself. And then on the right, I put 1 plus. What this means is that, okay, let me just present it neatly. This 1 minus, okay, what it means is a value that is slightly smaller than 1. Okay, whereas 1 plus will refer to a value that is a value slightly larger than 1. Okay, why 1? Because the base value is 1 itself. Okay, then we need to go and find out what is the dy over dx. Okay, for dy over dx, when x is equals to 1, I already know for certainty it must be 0. Because that is how 1 came about, right? Okay, so because x is equals to 1, such that dy over dx equals to 0, for great certainty we know this is going to be the case. Okay, and for the dy over dx to be 0, that means your gradient of the tangent must be a horizontal line, therefore the sketch must be a horizontal line. Okay? Right? Now what about the left and the right columns? What should we do? Okay? As mentioned, 1 minus actually refers to a value slightly smaller than 1. What we will choose to do normally, okay, is that just take 1 itself minus about 0.1 will do. Okay? Take a smaller value, okay, slightly smaller. Please don't jump one whole integer. I don't recommend that you choose 0. Because sometimes when you jump one big integer, okay, your graph itself, maybe at 1 integer away, is already on another side of the world already. Do you understand? Okay, so therefore we take something slightly small, and I find that 0.1 is usually good enough. Okay, so we choose in this case 0.9. Okay, minus 0.1. And then over here on the right side, we choose a value slightly larger. Typically, we choose plus 0.1. Okay, so that means I'll take 1.1 instead. So using the value 0.9, press into your calculator for 6x minus 6. So change your x to 0.9. Okay, and then see what is it that you get. Alright, so 6x, x being 0.9 minus away 6. Okay, and in this case, it should actually give you a negative value. Okay, so you just have to put the sign will do, right? You don't need to go and calculate the value. Just make sure you check your calculator. Okay, so press in, you should get a negative value. Okay, likewise on the other side, okay, press in x to be 1.1 for your dy over dx equals to 6x minus 6. And your value should actually be a positive value when you key into your calculator. So 6x minus 6, change the x to 1.1. Okay? By the way, in case your calculator is still on step mode, remember to change the mode, yeah? Okay? So you get 3 over 5, 0.6 over here, whereas the other one, you will get negative 3 over 5. Okay? So we just have to input the sign, and with the sign itself, I know that for negative means downward sloping, positive means upward sloping. So with the shape, the sketch, I will see that it is actually going in this manner. So I can confirm that it is a minimum point. Okay, so continuing the working. Therefore, I conclude 1, negative 2 is a minimum point. Okay? Questions? our first derivative test. Okay, we need to know what is the stationary point first. Build up our table. Alright, then after that look for values slightly smaller and slightly larger. Determine these two green parts here, and we can observe that it will be a minimum point. Okay? If no questions, I'd like you to give try 2 a try on your own. Okay? Do try 2 now. That will be on your textbook page 52. Okay, I give you 6 minutes to work on it, alright? If you still don't understand, please raise your hand, I'll come to you. We done? Yeah, I'll just write my answers for those that are done. You're able to get that the stationery points are at 1, 1, otherwise 2, 0. Okay. Then in part 3, we want to determine the nature of the stationery points. So we use our first derivative test. Okay. So we do point by point. At the point 1, 1, set up our table. Okay. If you don't have the habit of drawing the frame around your table itself, at least draw the lines that are inside now. Okay, no need to really frame it out. That's fine. Okay. So at the point 1, 1, our x value is at 1. To the left is 1 minus. To the right is 1 plus. Okay. Then naturally all of this should be 0 and then a straight line. Okay. For dy over dx on 1 minus, we put into our calculator the value 0.9, and you will find that it is a positive value, while this is a negative value for 1 plus. Okay? When dy over dx is positive, it means upward sloping. When it's negative, it's downward sloping. So therefore, using our first derivative test, I can conclude that 1, 1 is a maximum point. Okay, we can see that from the sketch itself. To be clearer, you can think of it like that. Okay? And then for the other point 2, 0, do the same thing again. Just that in our columns, we're looking at 2, 2 minus and 2 plus. Okay? And then we find that this will be negative, this will be positive, and we can conclude that 2, 0 is a minimum point. Okay. Questions? Okay, so like that is a minimum point. Okay, so having the sketch itself, it will help us to visualize how it will look like, whether is it maximum or minimum. Okay, so that is the good thing about your first derivative test. It gives you something visual. Okay, questions? If not, then I think I can only end here for today. Okay, tomorrow we'll continue with this. Then I'll go into our second derivative test as well. Yes, actually.